Hello and welcome to the session of Concept of Electrochemistry. In this session, we'll be learning about the electrochemistry and how it deals with the substances and how electrochemistry help in engineering applications. First of all, we'll recall what we have studied in the previous lessons that during redox reaction, the electrons pass from one substance to another. The flow of electron, which you called it as electric current, is used to do the work. Hence, electrochemistry is the branch of chemistry that deals with the conversion between chemical and electrical energy. There are two major branches in electrochemistry which we will examine in this session. One is electrochemical cell and the other one is electrolytic cell. Let us see the difference between these two cells. In electrochemical cell, the energy released is released by a spontaneous chemical reaction and converted into electrical energy. For example, batteries. In case of electrolytic cell, the electrical energy is used to cause a non-spontaneous chemical reaction to occur. For example, recharging the batteries and electroplating. The branch of electrochemistry deals with the chemical reaction which produce electricity and the changes associated with the passage of electric current through matter. When a chemical reaction is caused by an externally supplied current, as in electrolysis, or if an electric current is produced by a spontaneous chemical reaction, as in a battery, it is called electrochemical reaction. The chemical reactions where electrons are transferred directly between the molecules and or atoms are called oxidation-reduction reaction or redox reaction. In general, the electrochemistry describes the overall reactions, that is redox reaction, when connected by an external electric circuit and an intervening electrolyte. Hence, the electrochemistry is a study of process involved in the interconversion of electrical energy and chemical energy. Means electrical energy converted to chemical energy and chemical energy when it is converted to electrical energy. A substance which allows the electric current to pass through it is called a conductor. For example, metals, graphite, fused salt, aqueous solution of acid, base and salt. On the other side, a substance which does not conduct the electric current, that is, which does not allow the passage of electric current through it, are called insulators or non-conductors. The conductors are of two types, metallic conductor and electrolytic conductor. Let us see the difference between the two. In case of metallic conductor, the metallic conductor conducts electricity, but it does not get decomposed. In metallic conductor, there is a flow of electrons in the conductor and there is no change in the chemical property of the metallic conductor. The metallic conductor does not involve any transfer of matter and generally shows an increase in resistance as the temperature is raised. Whereas in case of electrolytic conductor, they conduct electricity but they also undergo chemical decomposition. It also involves the movement of ions in the solution or the infused electrolyte through which the current is produced. It also involves the chemical reaction at the two electrodes and transfer of electrolyte in the form of ions. Hence, generally, the electrolytic conductors, the resistance of the electrolytic solution decreases as the temperature is raised. The electrochemistry was given by Arrhenius. So let us see now Arrhenius' theory of ionization. A scientist named Arrhenius put forth in 1884 a comprehensive theory which is known as theory of electrolytic dissociation or ionic theory. An electrolyte, when dissolved in water, breaks up into two types of charged particles, one carrying a positive charge and the other carrying a negative charge. These charged particles are called ions. The positively charged ions are termed as cations and the negatively charged ions are termed as anions. As you can see here in the image, in the case of hydrogen chloride HCl, it get ionized into H plus and Cl minus. So when HCl is mixed with water in an aqueous solution, what happens? The hydrogen ion is formed and the chlorine ions are formed. The process of splitting of the molecules into ions of an electrolyte is called ionization. The next postulate of Arrhenius theory is that the cations are generally metallic radicals obtained by the loss of electrons from metallic atoms, while the anions are non-metallic atoms or the radicals. Basically, the radicals are the group of two or more elements. For example, if there is a metal, it will lose electron and form positive ion. And the non-metal will accept these electrons which are lost by the metal and it will form anion, the negative ion. The cations and anions carry equal but opposite charges. Ions are electrically charged atoms or radicals. The quantity of electric charge is equal to the valency of the atom or radical. As you can see in the animation that how the electrons are transferred from one electrode to other electrode. Here, there are two different types of half cell. One is having iron, another one is having copper. The electron is transferring from iron to copper. The iron rod is getting oxidized and the iron ions are getting dissolved in the solution. Thereby, they are releasing the electron and which gets transferred towards the copper electrode. Both the half cell is connected by a salt bridge which is KNO3 which forms the neutrality in both the half cell. When electron accept electron, when copper accept electron, the Cu plus 2 ion from the copper nitrate solution will get deposited on the copper electrode. The fraction of total number of molecules ionized in the electrolytic solution is known as degree of ionization. Hence, the degree of ionization is the number of dissociated molecules upon total number of molecules dissolved. The cations and anions present in the solution are constantly, ceaselessly reunite to form undissociated electrically neutral parent molecule and a state of dynamic equilibrium exists between the ionized and unionized molecule. For example, if AB is the unionized molecule, then it will get dissociate into A plus and B minus cation and anion. But this process is such that they constantly reunite to form undissociated. That means A and A plus and B minus both will again reunite to form AB unionized molecule. As shown in the example, you can imagine or visualize what exactly is happening. See here, the AB is converted into CD. Now CD is again further reunite with AB and from the original molecule. Because of this reverse reaction, the process of electrolytic dissociation is a reversible process. The property of the electrolyte in the solutions are the property of the ions produced. Hence, the next postulate of Arrhenius theory was that the ions are free to move and under the influence of electricity, they are directed towards the oppositely charged electrodes. The cation move towards the cathode, which is positively charged, and the anion move towards the anode, which is negatively charged. As you can see here in the image that the negative charged blue color ion are attracted toward the positive electrode and the positive charged ion purple color is attracted toward the negative electrode. Hence, the electrical conductivity of an electrolyte depends upon the number of ions present in the solution. Hence, the electrical conductivity increases as the ionization increases. So, when there is the electron loss, it is oxidation part, and when there is a gaining of electron, it is reduction part. And the flow of electron will give you the current. The next postulate of Arrhenius theory is that the electrolytes which gives the solution with high conductivity are called as strong electrolytes. That means which are completely ionized. For example, sodium chloride, hydrogen chloride, sodium hydroxide, sulfuric acid, etc. behave as a strong electrolyte. The electrolytes which are poor conductor in the solution are called weak electrolytes. That is, there is partial ionization. The conduction of an electrolytic solution generally increases with the increase in temperature, as the average kinetic energy of the ions increases as the temperature increases. Now let us see what are the different factors affecting the degree of ionization. As we know that a solution is made by dissolving a solute in a solvent. So the solute is when solute is added to the solvent, the particles are dissolved in the solution. They are evenly mixed in the solution, and once they are dissolved, they are not able to see. So we cannot see the solute particle if they are completely dissolved, and we get the solution. So therefore, the first factor which affects the degree of ionization is the nature of electrolyte, because it depends upon the solute and the solvent that whether the solute is completely dissolved in the solvent. If it is completely dissolved, then there is a good ionization in the solution. Hence, another factor will come now, nature of solvent. The solvent decide whether the solute is soluble or not. So the next factor is nature of solvent. Another factor is dilution of solution. If the solute is not dissolved in solvent in minimum quantity, then we have to increase the volume of the solvent so that the solute is completely dissolved. So dilution also affect the dissolving power of solute in the solvent and the degree of ionization. And the last factor is temperature. Because if the solute is not soluble in the solvent in large quantity also, then if we raise the temperature, sometimes the solute get dissolved in the solvent. Let us see how one by one each factor it affects the degree of ionization. The first factor, nature of electrolyte. As we have seen through Arrhenius postulate that some electrolytes are ionized to greater extent, and that is why they are strong electrolyte. But some electrolytes are ionized feebly, that is weakly, and that is why they are called as weak electrolyte. Hence, the degree of ionization of the electrolyte depend upon the extent of ionization, that is, whether they are strong or weak electrolyte. As we can see here that the sodium ion and chlorine ion are getting separated in the form of ion. So it depends upon the type of electrolyte whether they are completely ionized into cations or anions. The next factor is dilution of solution. The ionization usually increases with the dilution, and at a particular dilution the equilibrium is also attained when the rate of ionization is equal to the rate of formation of neutral molecules. The third factor is temperature of the solution. The ionization of an electrolyte increases with the rise of temperature due to collision of molecules in the compound. As the temperature, rate of collision is also increased. As the temperature increases, the rate of collision also increases. So, the attraction between the molecules in the compound is decreased and the bond is broken, and finally the degree of ionization increases. The another factor is the nature of solvent. The nature of solvent has a great effect to ionize the compound and is measured on the basis of dielectric constant of the solvent. The force of attraction of electrically charged ions in solution is weakened by dielectric constant. Hence, the polar solvent has high dielectric constant compared to non-polar solvent. So, the ionization is greater in polar solvent. Hence, water has high dielectric constant. Now, let us see what is the difference between the ionization and dissociation. Ionization is the process of separation of negatively and positively charged ions from the neutral atoms. The ionization of an electrolyte takes place either in solution or in fused state only, and the particles obtained during the ionization are electrically charged. The ions of the solution cannot be separated from each other as they are not stable in the form of ion on account of spatial attractive forces. Whereas in the case of dissociation, the dissociation is a process of separation of constituent units of a substance. The dissociation of substance takes place in any state and the particles obtained are electrically neutral and in a molecular state, stable state. Hence, the molecules obtained as a result of dissociation can be separated from each other. Hence, every chemical equilibrium can be characterized by an equilibrium constant known as KEQ. The KEQ and KP expressions are formulated as amounts of product divided by the amount of reactant. Each amount of the reactant or the product, either it is a concentration or a pressure, is raised to the power of its coefficient in the balanced chemical equation. Hence, the equilibrium constant K expresses the relationship between the product and the reactant of a reaction at equilibrium with respect to a specific unit. Suppose in an aqueous solution, the ionic equilibrium exists as AXBY plus N moles of H2O. Hence, it will give an reversible reaction with the product XA plus in aqueous condition and plus YB minus in aqueous condition. So, according to the law of equilibrium, the equilibrium constant Ke is given as product of concentration of the product and the upon the product of concentration of the reactant. Hence, for equation AXBY plus NH2O, we have Ke, the equilibrium constant, equal to concentration of A plus to the power X into concentration of B minus to the power Y upon concentration of AXBY, which is the reactant, into concentration of H2O, which is also the second reactant. Hence, where this braces indicates the concentration in moles per liter. Therefore, in an aqueous solution, the concentration now, with the assumption that in aqueous solution, the concentration of water is very large as compared to that of other component. Hence, the concentration of water at equilibrium is considered to be as constant value. Therefore, Ke multiplied by concentration of water to the power n will give you the concentration of A plus to the power x into concentration of B minus to power y upon concentration of AX By. Hence, the ionic equilibrium constant then it will be equal to the product of the two concentration of the two product upon concentration of the reactant, where Ki is the ionic equilibrium constant. This ionic equilibrium constant is greater for strong electrolyte and smaller for weak, constant for the strong base. Now let us see the ionization of weak acid and weak base. For weak acid, the complete ionization of acid in the aqueous solution will be For example, Ha is a weak acid in aqueous solution and it is forming H3O plus and A minus ion. Hence, again, according to the law of equilibrium, Ka is equal to concentration of A minus into concentration of H3O plus upon concentration of Ha. That is a weak acid, because now here we are considering the concentration of this reactant also, because it is a weak acid. So, hardly or feebly small amount of ions are disassociated. Therefore, Ka is equal to dissociation constant of weak acid. In weak acid solution, the acid is not completely ionized. So, here suppose that at initial time its initial concentration is C0. Hence, the amount of acid dissociated in time t is x moles per liter at equilibrium. Therefore, the equilibrium constant of undissociated acid will be the concentration of Ha, that is the weak acid, is equal to initial concentration minus the number of moles dissociated. Also, the concentration of positive ion and the negative ion are equal. Therefore, the dissociation constant for weak acid is equal to H3O plus into A minus concentration upon concentration of Ha, which will be again equal to, we are now substituting the ions with the concentration. So the concentration of H3O plus is X, and the concentration of A minus is also X, and the concentration of the starting material, that the reactant, is C0 minus X at 25 centigrade. Therefore, in a weak acid solution, there is only slight amount of ionization, and the concentration at equilibrium is equal to the initial concentration of the acid. So, we can assume that the concentration of the reactant, that is C0 minus X, is approximately equal to C0 only, because there is only feebly ionization in the weak acid solution. Therefore, Ka will be equal to concentration of X into concentration X upon C0, which is equal to X square is equal to Ka into C0, and the concentration we will be getting as, that is X equal to root of Ka into C0, which is equal to concentration of H2O plus at 25 degree centigrade. Hence, similarly it is for the weak base. Now let us see the ionic equilibrium constant for water. The self-ionization of water produces H plus and OH minus ion, and the number of water molecules attached to H plus is uncertain. Hence, the hydrogen ion is represented by either H plus or H3O plus. As the water is a poor conductor of electricity, that is, the conductivity is very low, but when dissolved ions are liberated, and there exists an equilibrium. For example, the 2 moles of water gives you H3O plus and OH minus ion. Therefore, the equilibrium constant of water can be written as Ke equal to the concentration of H3O plus into concentration of OH minus upon concentration of the reactant, that is H2O. But as the concentration of undissociated water is constant, we can assume the concentration of the reactant as a constant value. Therefore, Ke multiplied by the concentration of the reactant will give you the ionic product of water, a constant value, that is Kw. Hence, Kw is equal to H3O plus into OH minus ion, which is the ionic product of water. The value of Kw at 25 degrees centigrade is equal to 1 into 10 to the power minus 40. So, when Kw is equal to concentration of H3O plus into concentration of OH minus ion, which is equal to 10 to the power minus 14 moles per liter. Therefore, the concentration of H3O plus equal to concentration of OH minus, which equals to the half of 10 to the power minus 14, that is 10 to the power minus 7. Now what is pH? The pH stands for the potential of hydrogen ion. The negative logarithm of H3O plus ion to the base 10 is called the pH of the solution. It is the measure of the acidity and alkalinity of the solution. The pH value ranges from 0 to 14. As shown with the diagram, the pH value ranges from 0 to 14. 7 is the neutral condition. Below 7, it is acidic solution, means the concentration of H plus ion is more. Above 7, it is basic solution, that means the concentration of OH minus is higher. pH is find out with the formula pH is equal to minus log of H plus ion to the base 10, and if it is base, we can find the pH as POH is equal to minus log of OH minus ion to the base 10. So, if we convert pH into, if we want to find the concentration of H plus ion, what we will do, we will shift this log towards this left hand side, and it will become pH to the power minus 10. How? We are shifting this minus to this power along with this 10. So it will pH to the power minus 10. So if we want to find out the concentration of H plus ion, then it will be, suppose if the pH is, your pH is 2, then the concentration of H plus ion is 10 to the power minus 2. Hence the pH is written as 10 to the power minus pH. This minus sign is shifted here. Similarly, if we talk about POH, if we shift this log to the left hand side, what will happen? And the minus sign also, it will be 10 to the power minus POH. So suppose if your POH value is 7, pH value is 7 or 8, then it will be written as, the concentration will be written as 10 to the power minus 8, 10 to the power minus 9, or so on. The concentration of the solution is given as moles per liter. The pH value is important in various fields, such as in agriculture field for knowing the pH of soil and clay. In biomedical field, it is useful to know the nature of blood and urine. In chemical laboratory, we use the pH to know the solution if it is acidic or basic or neutral. In electroplating industry, to get the smooth and uniform deposits, that is the pH of the bath should be maintained. In the city water supply, the pH of potable water should be maintained near about 7.5. Now, what is buffer solution? The solution which resists the change in pH of the solution when a small amount of acid or base is added to it is called the buffer solution. The buffer solution is made by mixing the solution of weak acid and a salt of that weak acid, which is called acidic buffer solution. The buffer solution made by mixing the solution of weak base and a salt of weak base is called basic buffer solution. As shown in the example, here is an example of acetic acid, which is a very weak acid and which is very feebly ionized. So, if we add a base or an acid to this solution, what will happen? This buffer solution is made by the weak acid. This is the weak acid and this is a salt of weak acid. So, what will happen when if we add acid or base? The hydrogen ion will react with OH minus ion and it will form water, and the acetate ion will react with the hydrogen ion and it will form acetic acid. So the pH of the solution will remain same. Either it will form the weak acid only or either it will form the salt only. Let us see an example, acidic buffer mechanism. Suppose acetic acid is a weak acid and it get ionized into CH3, COO minus and H plus ion. And the salt of weak acid is sodium acetate, with which we have made a buffer solution, acidic buffer solution. And this salt will also get ionized into CH3, COO minus plus Na plus ion. Now if HCl is added, then HCl is also ionized into H plus and Cl minus ion. So this H plus ion will get react with the common ion, that is acetate ion, and the sodium ion will get react with chlorine ion. Ultimately, the pH of the solution will remain the same because NaCl is neutral and CH3 COO minus, it will form the same weak acid. So the pH will not change. And on the other hand, the H plus also combine, if the H plus combine with Cl, then it will again form the HCl. So the pH remain the same. Suppose if NaOH is added, then NaOH is also ionized into Na plus and OH minus ion. In this case, the sodium ion will react with the common ion, that is the acetate ion, and will form the sodium acetate. Hence the pH remains the same. And on the other hand, the OH minus ion will react with Na plus ion, which will again form the base, which you have already added with the same pH. And the hydrogen ion, when it combines with OH minus ion, it will form a neutral water. Similarly is the mechanism for basic buffer. For example, ammonium hydroxide is a weak base and it will get ionized into NH4 plus ion and OH minus ion. The salt of ammonium hydroxide, that is the salt of weak acid to make the buffer, is ammonium chloride, and it also get ionized into NH4 plus ion and Cl minus ion. Now what happen if we add HCl in this basic buffer solution? Again, the HCl get ionized into H plus ion and Cl minus ion. So the H plus ion formed from HCl will get combined with OH minus ion and form the water. Or it will get combined with Cl minus ion and it will form ultimately the hydrochloric acid only, which we have added. So the pH remains the same. On the other hand, the chlorine ion will get combined with NH4 plus ion, the common ion, and it will form the salt of that weak acid. So again the pH remains the same. Similarly, if we add a base to this buffer solution, basic buffer solution, then the NaOH will also get ionized into Na plus ion and OH minus ion, which ultimately get react with OH and form NaOH only. So the pH remains same. And again, it can also react with Na plus and Cl minus to form a neutral salt. The hydroxide ion, when combined with the common ion, it will form the weak acid. So again the pH of the solution remains the same. There is no change in the pH of the solution when we add a buffer to acidic solution or a basic. Now let us see what is electrolyte and non-electrolyte. An electrolyte is a solution made by mixing solute and solvent where they ionizes into cations and anions. For example, a salt of sodium chloride when dissolved in water ionizes into sodium ion and chlorine ion. In an aqueous solution, the electrolyte exhibit the following important properties. They exhibit anomalous colligative property. They can conduct an electric current. They tend to show rapid chemical reactions also. The electrolytes can be classified as strong electrolyte and weak electrolyte as we have seen earlier, depending on their ability to ionize in the aqueous solution. The strong electrolytes are the substances that are completely ionized in the water, and the weak electrolytes, in contrast, are the electrolytes which ionize only partly or feebly in the water. The other type of electrolyte is non-electrolyte. Non-electrolytes are the substances that do not ionize in the water at all, and therefore they do not conduct an electric current in the solution. For example, they include sucrose, fructose, urea, and glycerol. Electrode. The, an electrode is a conductor which passes or allows to flow the electrons from one end to the other end. The electron can be defined as a metal strip or a rod dipped in electrolytic solution of its own ion and on whose surface the oxidation and reduction reaction takes place is called electrode. They are mainly of three types: active metal electrodes, for example zinc, copper, etc., and the inert electrode of metal or non-metal, for example platinum, graphite, etc. And the third type of electrode is gaseous electrode, which includes, for example, hydrogen gas electrode, chlorine gas electrode. Based on the electrode dipped in the solution, half cell. What is half cell? The electrode and the solution in which it is dipped is collectively known as half cell. The half cell is constructed by dipping the metal or non-metal strip into an electrolytic solution of its own ion. The representation of the half cell is shown by inserting a single vertical line between an electrode and active ion. As shown in the diagram, in the first image, a zinc electrode is dipped in a solution of ZnSO4. So this makes one half cell, which is oxidation half cell. Why oxidation half cell? Because it is getting oxidized. The electrons are released. It acts as anode. On the other side, the other half cell, the copper electrode is dipped in a copper sulfate solution, where copper can act as cathode by gaining the electron. So it is called as reduction half cell, where the copper gains the electron and form copper. So the equation is written as or represented as: if the element goes oxidation, means the electron is lost, then the solid is written first, oblique, then the ion formed is written because the electron is lost. And in case of reduction half cell, it is written as the ion is written first, and by accepting the electron, the solid is formed. So the ion portion is written first, oblique, then solid copper. As we can see here in the animation, that the zinc anode is behaving as oxidation half cell. Here the zinc electrode is getting deteriorated or oxidized, and the Zn+2 ion is released in the solution. As the Zn plus ion is released into the solution, the electron is transferred through this outer external electric circuit towards the other electron. The electron transferred to other electrode is copper, which behave as cathode. That means it gains the electron through the external circuit. And from the solution, copper sulfate solution, the Cu2 plus ions are get deposited by accepting these electrons. As you can see here in the second image, the copper ion from the solution accept the electrons from the outer circuit and get deposited on this copper cathode. So, based on the loss of electron and the gain of electron, that is the oxidation reduction half cell or the oxidation reduction reaction, as the number of electrons are transferred from one end to another end, we can find out the electrode potential and the electromotive force of the cell. So the electrode potential is defined as the measure of tendency of a metallic electrode to lose or gain electrons when it is in contact with a solution of its own salt of unit molar concentration at 25 degree centigrade. The oxidation potential. So the electrode potentials are of two types: oxidation potential and reduction potential. Oxidation potential, the tendency of an electrode to lose electron, is a direct measure of its tendency to get oxidized, and this tendency of electrode is called oxidation potential. Whereas reduction potential is the tendency of an electrode to gain electron in a direct measure of its tendency to get reduced, and this tendency of electrode is called as reduction potential. The electromotive force. When two half cells are coupled with each other, then the difference of the potential, that is difference in the oxidation and reduction potential, which causes a current to flow from the electrode to higher electrode of higher potential to one of the lower potential is called the EMF of the cell, which is expressed in volts. So when a metal is in contact with its salt solution, then the following mechanism takes place. It loses the electron and form positive ion, which is called oxidation reaction. And the other side, the non-metal will accept this electron and gain the electron and form the single metal, which is called as a reduction reaction. Thus, a dynamic equilibrium exists in the reaction due to the formation of negative or positive charge developed on the metal, which attracts the positively or negatively charged free ions in the solution. And due to this attraction, the positive or the negative ions remains close to the metal. Therefore, a potential difference is developed between the metal and the solution. Hence, at equilibrium, the potential difference between the metal and the solution becomes a constant value. With respect to this knowledge, now we will see what is reference electrode. The electrode which have standard potential value and with which we can compare the potential of an other electrode is called reference electrode. The best reference electrode is a standard hydrogen electrode whose electrode potential at all temperature is taken or considered to be at zero. The other example of reference electrodes are silver electrode, glass electrode, and many more. Let us see one type of reference electrode, that is standard hydrogen electrode. In short, SHE, a redox electrode. It consists of a small platinum foil about 0.5 centimeter to 0.5 centimeter, which is sealed through the end of glass tube. This glass tube is surrounded by another coaxial tube, which is sealed to the inner glass tube at the top. The outer glass tube has a side arm for passing hydrogen gas into the space provided. The bottom of the outer tube is of bell shape. The platinum foil is coated with the layer of finely divided platinum black. This platinum foil This platinum foil absorbs the hydrogen gas and also speed up the equilibrium between the hydrogen gas and the hydrogen ion. So here you can see that the platinum electrode absorbs the hydrogen gas converted into H plus ion. The platinum electrode, when dipped in one normal HCl solution under 1 atmospheric pressure, the hydrogen gas is passed through from a normal or a standard hydrogen electrode. The EMF of such a cell has arbitrarily the value 0 or at 0. Now, with respect to this reference electrode, we can find the potential of other electrode. For example, the standard hydrogen half cell paired with a copper electrode. So to measure the electrode potential of copper, it is paired with standard hydrogen electrode, and as the reaction is passed, the mass of copper is increased with respect to time. The half cell of the reaction of copper electrode and the reference electrode is like copper after gaining 2 electrons will form copper and it becomes cathode, whereas the standard hydrogen electrode, that is a reference electrode, become as anode. So as per the potential obtained from the EMF of the cell is EMF of cathode minus EMF anode. So now, when a reference electrode is connected to another electrode of which we have to find the potential, the reference electrode voltage is 0.00. So, in the voltmeter, the deflection shows the value of the unknown electrode. Electrochemical cell. An electrochemical cell is a device in which a redox reaction takes place to convert the chemical energy into electrical energy. It is also called as voltaic cell or galvanic cell. Let us see the construction of electrochemical cell. It consists of two half cells connected with a salt bridge. One half cell consists of zinc electrode dipped in a solution of zinc sulfate having concentration of 1 molar at 25 degrees centigrade at 1 atmospheric pressure. On this electrode, oxidation reaction takes place. That is, the zinc ion gets ionized into Zn2 plus ion and releases or loses 2 electron and becomes the anode where oxidation takes place. Another half cell consists of copper electrode dipped in the solution of copper sulfate having concentration of 1 molar at 25 degrees centigrade at 1 atmospheric pressure. On this electrode, the reduction reaction takes place and the copper ion gains 2 electrons and converted into copper, which behave as. Let us see the schematic diagram of the electrochemical cell. As shown in the diagram, the first half cell, zinc electrode is dipped in the ZnSO4 solution, and in the second half cell, copper electrode is dipped in copper sulfate solution. Both the half cell is connected with the salt bridge and the electrodes are externally connected with the meter. So when the reaction takes place, the Zn ion moves into the solution and the electrons are transferred to the other electrode from the external circuit, and the copper ion from the copper sulfate solution gains these two electrons and get converted into copper. So one is oxidation half cell and the other one is reduction half cell. The representation of the electrochemical cell is given as anode 2/cathode. This particular symbol represents your salt bridge. Here it is a expanded form how the zinc ion gets separated into and dissolved in the solution and the 2 electrons are lost per zinc atom due to oxidation. And here how copper ion from the solution gains a 2 electron and get deposited on the electrode. So one is oxidation half cell and the another one is reduction half cell. And the overall cell reaction will be zinc plus copper will give you zinc. From zinc you will get Zn plus 2 and from Cu plus 2 you will get Cu solid. Let us see the function of salt bridge. It is used to connect the oxidation half cell and the reduction half cell. It maintains the electrical neutrality within the internal circuit of two half cells. It maintains the charge balance between the two half cells as the electron moves from one electrode to the other electrode. It also prevents the accumulation of positive and negative charge near the electrode. Working of a salt bridge. In the oxidation half cell, the anode generates the electrons and positive ion. Hence, the electron will flow through the external circuit toward the reduction half cell, leaving behind the positive ion in the solution. So, in order to maintain the electrical neutrality in the oxidation half cell, the negative ion from the salt bridge moves towards the half cell where the positively charged ions are there. Similarly, the same phenomenon happens in case of reduction half cell and the neutrality is formed. Electrolysis. The chemical change caused by the passage of an electric current or through a solution of an electrolyte is called electrolysis, or it can be defined as the process in which an electric current is passed through the solution of an electrolyte and due to the passage of electric current, the cations and the anions move towards their respective electrode, which is called as electrolysis. As we can see in the diagram, the positive ion is attracted towards the negative electrode and the negative ions are attracted towards the positive electrode. In case of electrolysis, the current is induced to happen the chemical reaction. Whereas in case of electrochemical cell, the chemical reaction induced to give the current. In an electrolytic cell, the external source of voltage is used to bring about a chemical reaction. The electrolytic cell converts the electrical energy into chemical energy, and there is only one cell containing both the electrodes, anode and cathode, in one cell, which are coupled with external DC current to induce the current in the cell having the electrolyte of one of the electrode component in common. Applications of electrolysis. So electrolysis is used in purification of impure copper, which is also known as electrorefining. In this process, the metals are purified by electrolysis method, which is called electrorefining, as shown in the animation. The impure copper block of copper metal is connected as anode and the pure copper sheet is used as cathode, and the aqueous solution of copper sulfate is used as electrolyte. Then on passing the current, the impure copper from anode gets separated through oxidation and goes into the solution, and the equivalent amount of copper ion from the solution get deposited on the cathode in the pure form. Hence, the weight of anode decreases and the weight of cathode increases. The other impurities are collected at the bottom of the anode, which is called as anode mud. The electrolysis is also used in extraction of magnesium. A mixture of 50 parts of potassium chloride, 25 parts of sodium chloride and 15 parts of magnesium chloride is heated in an iron crucible at 700 degrees centigrade to get fused mixture. The electrolysis is carried out by using iron crucible as cathode and cylindrical graphite covered with the china clay tube as shown in the figure. At anode, the chlorine gas come out through the china clay tube, and at cathode, the molten magnesium metal is collected. To protect this collected magnesium metal by air oxidation, atmosphere of coal gas or hydrogen gas is maintained on the surface of the magnesium. Electrolysis is also used in the process of electroplating. The process of coating of an inferior metal with a superior metal by electrolysis is known as electroplating. With the help of electrolysis, the coating of chromium, nickel, zinc, tin can be applied on iron article. As shown in the animation, we can have a look that a copper is taken as anode and a brass is taken as cathode. So when the current is passed, copper gets into the solution and get deposited on the brass electrode. Similarly, if there is a coating of zinc, then it is called galvanizing. If there is a coating of tin, it is called tinning. If there is a coating of chrome, it is called chrome plating. And if there is a coating of nickel, it is nickel plating. The other applications of electrolysis are production of hydrogen by electrolysis of water, manufacturing of heavy water, the metals like sodium, potassium, magnesium, aluminium, etc. are obtained by electrolysis of fused electrolytes. Non-metals like hydrogen, fluorine, chlorine are obtained by electrolysis. Through electrolysis method, the pure metal is deposited at cathode from a solution containing the metal ions. And also the compounds like sodium hydroxide, potassium hydroxide, white lead, etc. are synthesized by electrosynthesis of charge. Now let us see Faraday's second law of electrolysis. When the same quantity of charge is passed through a different series of electrolytic cell containing different electrolytes, then the amount of product obtained at different electrodes are directly proportional to their equivalent weights. As shown in the diagram, there are three electrolytic cell connected in series. One is dilute sulfuric acid cell, copper sulfate cell, and silver nitrate cell. Now, according to the first law, the amount of element deposited on the electrode is directly proportional to the amount of charge passed. So W is equal to E into Q. Now, Then Q is equal to 96,500 coulomb, where W becomes gram equivalent mass, that is the electrochemical equivalent will be equal to Z into 96,500. Therefore, Z is equal to E upon 96,500, and hence the ratio of two electrolytic cell connected in series will give the electrochemical equivalent of the cell. Nernst equation for a cell reaction. The electrode potential and the EMF of the cell depend upon the nature of the electrode, temperature, and the activities, that is the concentration of the ion in the solution. This equation shows a relation between the potential of non-standard electrochemical cell and the concentration of the solution. Hence, it is known as Nernst equation. The concentration of all species involved in the electrode reaction may be unity, but the electrode potential at any concentration measured with respect to standard hydrogen electrode can be represented by EMF of the cell is equal to E0 minus RT upon NF into natural log of Q, where E of the cell is cell potential of the cell, E0 is the cell potential under standard conditions, R is the universal gas constant, T is the temperature, and is equal to number of electrons transferred in the redox reaction, F is equal to Faraday's constant, Q is equal to reaction quotient. So the calculation of single electrode reduction potential from standard single electrode reduction potential for an atom or ion is given by the Nernst equation. This Nernst equation is applicable to find for a reduction reaction, that is Nernst equation for a single electrode. The reduction potential for a reduction reaction can be, suppose if Mn plus plus electron will give you n moles of M. Therefore, the reduction potential will be equal to concentration of Mn plus upon M, which is equal to the EMF of the cell of reduction potential, which is minus 2.303 RT upon NF log of 1 upon reduction concentration of reduction electrode, where R is the gas constant 8.314 joule per mole, T is equal to absolute temperature, N is equal to number of mole of electrons involved, F is equal to 96,487, which is approximately equal to 96,500 coulomb per mole, which is equal to the charge carried by 1 mole of electron, and concentration of N plus Mn plus is equal to active mass ions. So this Nernst equation can be used to calculate the single electrode reduction or oxidation potential at any condition, to calculate the standard electrode potential, to compare the relative ability as a reductive or oxidative agent, and to find the feasibility of the combination of such single electrode to produce electric potential. The Nernst equation is also used to find the EMF of an electrochemical cell and to find the unknown ionic concentration. The pH of the solution and the solubility of sparingly soluble salt also can be measured with the help of Nernst equation. Hence, with the concept of this electrochemistry, we can apply or we can use this electrochemistry in different fields like sensing, corrosion, organic electrosynthesis, industrial electrolysis, energy conversion, energy storage, and many more.